All right, here we go. I anticipate getting criticized as a crackpot, and I am arguably doing nothing more here than posting weird science videos on YouTube. Currently, international stability is predicated in terms of pure physics upon a few things. First, the world is covered with nukes. Events such as the 2017 Tic Tac footage are akin to a Sputnik moment, where scientific and technological breakthroughs will follow in light of the demonstration of proof of concept independent of the known origin or purpose, you could say, of the Tic Tac observable. This is obviously a huge, massively difficult open problem, and I am a nobody. This depends, of course, on the holographic or interdimensional extent and nature of reality. Maybe what it takes is merging computational group theory and computational partial differential equations to simulate radiating different crystal material structures and assessing whether novel physical results arise. Oh. Smooth like a manifold, another tensor transform, take a covariant derivative, no point unexplored, like a light cone in a dream, on the consciousness stream, but it's all a tricky scheme to get you.
To take your call.
So, you're a philosopher?
Next. So the effects are consistent with a mid-air thermonuclear explosion with fission boosting of enormous yield.
Bonjour tout le monde. Welcome back, Differential Geometry Gang. If you're new, I'm Anthony, obviously. Thank you to everyone for liking my video on the way in, because that helps encourage the YouTube algorithm to look favorably on my content as a small channel. I am not a mathematician, I am not a scientist, this is not a class, this is not a course, this is not a podcast, this is not a lecture series, and this is not necessarily a math audiobook. But this is reading the book, Differential Geometry by Erwin Kreisig, out loud. Some people watch this to fall asleep or passively in the background at work. Maybe you watch only the beginnings of some of my videos. Maybe you've watched every video on my channel in its entirety. Some of you may only listen to the audio of these episodes, and shout out to everyone who only listens to the audio. Either way, I appreciate you stopping by, and I also encourage everyone who wants to comment down below. It could be related to this video, it could be a question or not, but if you do comment, your comment could be featured as the comment of the week in a future episode. Next, we have the figure 69 cone t-shirts, which I announced last fall in the third fundamental form video. And earlier this year, so after I said, hey, I'm going to make these shirts, but then earlier this year, I said that when I launched them that I would do a giveaway if you filled out this survey. And today is the day that I'm announcing the winner of that giveaway. So if you didn't fill out the survey, head over to anthonymakesvideos.com/merch. You can get yourself a figure 69 cone t-shirt, short sleeve in either black or purple. And I also put the logo on a black long sleeve sweater. So cop one of those. And if you did fill out the survey, first of all, thank you. There aren't enough people to start a Discord or anything like that yet, but when I do, you guys will obviously hear about it. And without any further ado, I am now going to select the winner of the figure 69 cone t-shirt giveaway. So I made up an alias based upon the email addresses that were used in the survey, and I assigned a number to everyone. So since exactly 6 people filled out the survey and entered the giveaway, I'm now going to roll virtual dice to select the winner. So, all right, so we have, in no particular order, these are the names. We've got The Ocean, we've got Thomas, we've got Mr. Abbas, we have Bjorn, and then we have Learn, L-E-R-N, and then we have Angel. And those are 1, 2, 3, 4, 5, 6 respectively. So here we go. This is the atmospheric noise random number generator, because as we all know here on this channel, there's no such thing as truly random code, but we're gonna roll 1 die here. And that's 2, so that goes to Thomas. So congratulations, Thomas. By the time you're watching this, if you even watch this, I will have hopefully already reached out to you. Yeah, so everyone else who already answered the survey, I won't forget that you guys once said that you're interested in these shirts, but everyone should head over to anthonymakesvideos.com/merch and get yourself a figure 69 cone t-shirt. And with that, let's get started. All right, here we go. So, specifically at the point in the reading which these episodes are up to, which is chapter 8 from Differential Geometry by Erwin Kreisig, rest in peace. The current chapter is titled Special Surfaces, which starts off by introducing so-called minimal surfaces. So, for a quick review, curvature is a big deal in differential geometry. Consider the surface of a sphere, for instance. Analogously to Euclid's first postulate, if you picked any 2 points on the surface of the sphere, a rubber band can be wrapped around the sphere so that the rubber band crosses the 2 given points. Defined in the ambient space of the problem, the function for the path along the rubber band connecting the 2 given points defines a geodesic on the surface of the sphere. Keep in mind that geodesics also are intrinsic to the surface's geometry. Allowing general surfaces then besides a sphere to be possible, then consider a general surface and pick a given point. What's the curvature at this point, you might ask? One possibility of defining, finding, measuring this curvature, assigning a number to this word that we're using, curvature, one possibility is to first find the magnitude of the tangent vector for every geodesic emanating from this given point on the surface. Second, pick the direction of the geodesic whose tangent vector has the largest magnitude. So you're looking at the direction of the geodesic with the steepest increase or decrease, depending on how you look at it. And you're going to call this direction the first principal direction. Step 3. Take the orthogonal direction to the first principal direction from the previous step. Now, in a scenario that's higher than 3-dimensional, the key seems to be to repeat until you have enough principal direction vectors to form a suitable linearly independent basis for a vector space with the same dimension as whatever the surface really involved has. Step 4, construct a normal section to the surface along each principal direction. Fifth, construct an osculating circle, or basically like a tangent circle, so it's only touching the curve of the surface at one nominal point. So construct an osculating circle along the curve of the normal section of the surface. Sixth, measure the radius of that osculating circle or tangent circle. Seventh, take the reciprocal of this radius for the principal direction as the corresponding principal curvature on the given surface at the given point along the principal direction. Finally, you repeat these steps for all of the principal directions that you had found, depending on whatever dimension space you're working in, so that one has thus obtained a set of principal directions and corresponding principal curvatures at the given point on the given surface. Now, you have all these principal curvatures, corresponding principal directions. If you take the principal curvatures and you multiply them all together, now you have what's called Gaussian curvature. And Gaussian curvature is considered very classical because, as I've shown in an expository document which you can download from the files page on my website, so go to anthonymakesvideos.com/files, and it's under the Riemann header. But you can find this document where I showed that Riemann, Bernard Riemann, would go beyond his mentor Carl Friedrich Gauss's notion of curvature, and the concepts that Riemann would use to do so are the basis for what's now referred to as Riemannian geometry. Now, instead of multiplying all the principal curvatures together, you could take the arithmetic mean of all your principal curvatures that you found for this given point on the given surface. And by the way, you could really repeat this for every point on the surface, or you could repeat it for all of the points in a curve along the surface, what have you. But the arithmetic mean of principal curvatures is referred to simply as the mean curvature at a given point for a given surface. So a minimal surface then is a surface whose mean curvature is 0 at every point. Furthermore, we have these other kinds of surfaces, which I've talked about in a previous episode, that are called ruled surfaces. And ruled surfaces are surfaces such that through every point on the surface, there is a straight line, or you could call those straight lines a ruling, that lies on that surface. So a type of ruled surface that we could possibly have is a so-called conoid. And a conoid is a particular kind of ruled surface whose rulings satisfy two conditions. Namely, 1, all rulings are parallel to a plane, which is called the directrix plane. And 2, all rulings intersect a fixed line, which is imaginatively called the axis. Go figure. Furthermore, a conoid is a right conoid if its axis is perpendicular to its directrix plane. And I bring all this up because in the next section that I'm going to read is section 81, which is titled Examples of Minimal Surfaces. And specifically, the examples that it brings up are the catenoid and the right helicoid. So basically in section 81, this is like foreshadowing for what's going to come up. There are 3 theorems which show that the catenoid and the right helicoid are unique minimal surfaces within their respective classes. So namely, catenoids are classified as surfaces of revolution. So catenoids are unique minimal surfaces of the classification of surfaces of revolution. And then right helicoids are, of course, classified as right conoids. So right helicoids are minimal surfaces in the overall group of right conoids and are unique. But furthermore, the third theorem shows that catenoids and right helicoids are isometric, and therefore a catenoid can be bent into a helicoid. So, going beyond classification with the mathematical bending that we can show. As a matter of fact, the problems reinforce this by finding the representations of the right helicoids which are isometric to a catenoid, and then tracing the mapping of the smallest circle of the catenoid to the helicoid's axis. But first, a SOAP example. A common example of a physical model of an area minimizing minimal surface is the surface made by a soap film with some given frame shape or frame geometry. The science of soap bubbles and soap films is an entire rabbit hole, and if you want to dive down that, I recommend this book down below here, The Science of Soap Films and Soap Bubbles by Cyril Eisenberg. It's not just mathematical, it has scientific stuff, which might be interesting to some people. But here is a memorable soap-related math illustration to the left here from Geometric Measure Theory, Science of Soap Bubbles and Soap Films by Frank Morgan. And Frank Morgan, the author, is here pictured to the left of this interesting illustration as a young boy here. But the illustration to his right is this interesting illustration that I want to emphasize here. So the point of this figure is that finding minimal surfaces isn't as straightforward as one might hope. Consider the direct method for finding a surface of least area with a given boundary. This has 3 steps, namely, 1, you start with a sequence of surfaces with areas decreasing to the greatest lower bound or the infimum of the sequence. Step 2 is to extract a convergent subsequence from that sequence. And third, you show that the limit surface is the desired surface of least area coming out of that convergent subsequence. However, this figure illustrates how this method breaks down. Even when the boundary is the unit circle, since the closed and boundedness conditions of compactness aren't fulfilled, the surfaces don't settle down, you could say, to the flat disk with the prescribed area, even if their areas do approach your intended value, which in this case might be pi, as in the case of the figure. So in fact, by developing wild irregular shapes that don't converge neatly, like sending out thin tentacles of sorts toward every rational point, you could say, then the sequence just described that sends out all these thin tentacles to all the rational points in the space could then include all of 3-dimensional real space in its closure. So in a realistic physics setting, some would call this mathematical effect bubbling, but I think the purely mathematical illustration here really drives the point home. And there are plenty of other really striking illustrations, I guess you could say, from the Geometric Measure Theory book. So check that out if you want. I also put in here a minimal surface represented by the soap film on a single spiral helix wireframe here. And then a little bit to the right of the Science of Soap Films book, we have this geometric pattern from a soap bubble foam, which is kind of interesting. This is all kind of just to like get your mind jogging for like some of the stuff that's coming up here. Because I don't know if you've realized, this is like my video at the beginning of the year. This is like another 10,000 words, 30 pages here. So buckle up for the math, right? And in front of the geometric soap bubble foam, we have a technically correct depiction of a double bubble. And so I guess like in this field of soap films and soap bubbles, I guess, the technical definition of a double bubble is technically you have 3 spherical surfaces and they meet at 120-degree angles on a common circle, or I guess if you're in 3-dimensional space, then three-dimensional space, then it's a common sphere, right? But the double bubble theorem thus states that the shape that encloses and separates two given volumes and has the minimal possible surface area is the double bubble, which I just described and have depicted here in the bottom right-hand corner. So, like I said, this is like a technical distinction, I guess, and believe it or not, it is going to come up later. So here is the too long didn't read of what's up next before I delve into the reading. So in the previous episode 15 of this series, I was only a third of the way into the differential geometry book at the time, and my talk in the beginning of the video was motivated by asking two questions. The first is, why bother learning about differential geometry at all? And that question should really read, what sort of real-world applications of differential geometry are there? But I guess it's kind of foreshadowing, because my answer to the first question is the same now as then. General relativity is a worthwhile application of differential geometry. So Einstein, of course, used differential geometry as the mathematical language for his general relativity, which is basically a theory of gravitation. But this all begs the question, which I also asked in that previous episode, how did physics get there? Or how did a theory of gravitation come to be posed in terms of differential geometry? The short answer is that before Einstein, theories of gravitation were driven by observations of gravitational phenomena like falling objects and planetary motion. Einstein's general relativity, on the other hand, is driven by insights in geometry, thus reframing the force of gravitation as a phenomenon emerging from curved spacetime. This, of course, led to the development of the Einstein field equations. The solutions of these equations both accurately fit centuries-old data observing the precession of Mercury's orbit and predict the degree of gravitational lensing observed in a constellation behind a solar eclipse, in each case with a greater degree of precision than Newton's theory of gravitation. With his eponymous field equations, Einstein showed that the gravitational potential corresponds to the coefficients of an invariant quadratic differential form akin to the Pythagorean theorem in curved spacetime. It's kind of like an extended, generalized Pythagorean theorem. While Einstein's formulation is seemingly radical, Newton's law of gravitation is actually a low-energy, weak field limit of general relativity, thereby unifying the two seemingly disparate frameworks of Pythagoreanism and Newtonian mechanics. Next question is, what sort of real-world applications of general relativity are there? And an obvious and relatable answer is GPS. Now, unlike Newton's theory of gravitation, which is ignorant of relativistic effects, general relativity actually accounts for effects like the subtle warping of spacetime. In a weaker gravitational field, by virtue of being at a greater distance from the center of the Earth than its surface, an orbiting satellite will experience time dilation, whereby the satellite's clock will tick faster than the clock in a receiver on Earth. In the context of GPS, Newton's theory of gravitation doesn't have an answer for these systematic timing inaccuracies between the satellites and receivers. The timing inaccuracies cause distance errors proportional to the speed of light, leading to rapidly accumulating errors that make Newtonian GPS impractical. Classical Newtonian mechanics only GPS, after around 10 minutes, could be an error roughly on the scale of tens of meters, and after around a day, the error could be roughly on the scale of tens of kilometers. General relativity provides a framework that explains these effects and informs adjustments that enable GPS to work in a way that is practical. For the rest of this intro, I'm going to revisit ideas from these questions which I brought up in earlier episodes, but I'm going to clarify them with my perspective now that I'm nearly at the end of the book. This book is upside down. I was probably holding it upside down earlier. Now, I've mentioned before that one of the running themes of this series is the interplay between math, physics, and philosophy. I'm obviously a bit biased towards the math. However, math alone is sterile. Hermann Weyl once said that inasmuch as the mathematician operates with his conceptions along strict and formal lines, he, above all, must be reminded from time to time that the origins of things lie in greater depths than those to which his methods enable him to descend. Beyond the knowledge gained from the individual sciences, there remains the task of comprehending. In spite of the fact that the views of philosophy sway from one system to another, we cannot dispense with it unless we are to convert knowledge into a meaningless chaos. Indeed, it seems as though the history of physics and math so far has been not unlike the two entwined snakes around the staff of Caduceus, each driving the other to new heights of progress. But in addition, the interpretation of problems in physics and math can often get deeply philosophical. Think of dialectic. The term dialectic here refers to a dynamic process, a motor, if you will, of negation and preservation that serves as a philosophical mechanism for uncovering truth. Consequently, advancements in physics, mathematics, science, and technology can be understood to unfold dialectically. In previous episodes, I've brought up Copernican heliocentrism because it was a revolution in how people understood the world that incorporates a mixture of elements of math, physics, and philosophy. So the question is, why was Copernicus' astronomical model not regarded as merely changing minor premises in Ptolemy's more established model at the time? One part might be that the gains in accuracy afforded by Copernicus' mathematical model fitted to astronomical data also changed the foundational assumptions of Ptolemy's prevailing framework. This, in addition to the metaphysical turn, is what I think makes it the Copernican revolution. Further down the road, however, a similar revolutionary gesture would be made by Isaac Newton. Neither the Earth nor our Sun are the center of the celestial model for Newton. Instead, Newtonian spacetime is God's boundless sensorium, a theater of existence of the real world and matter as its substance. It's like Shakespeare said, "All the world's a stage, and all the men and women merely players. They have their exits and their entrances, and one man in his time plays many parts." Around the same time Newton was around, in 1710, philosopher George Berkeley, who I've mentioned before, published a treatise concerning the principles of human knowledge, in which he famously claimed, "Esse est percipi," which means to be is to be perceived. Probably didn't get the pronunciation 100% on that, but perhaps you've been asked before, if a tree falls in a forest and no one is around to hear it, does it make a sound? Now, Berkeley did not originate that specific question, but it's attributed to him because it encapsulates what's known as subjective idealism. Berkeley would answer that there is no sound, and he would go even further and say that no material world exists independently of perceptions, that objects are collections of ideas in minds, and that reality is sustained by God's divine consciousness in the absence of human observation. Dr. Manhattan from The Watchmen, during his philosophical musings, would state his own metaphysical position as, "Perhaps the world is not made. Perhaps nothing is made. Perhaps it simply is, has been, will always be there. A clock without a craftsman." Conversely, as Leibniz said, God does not need a sense organ to perceive objects, and that space is merely the aggregate of all relations between objects and is not a self-subsistent reality. I've mentioned this before already, but it'll be relevant again later in this video, but I think if Leibniz were here today and he grasped our current technology, he might subscribe to the simulation hypothesis of reality. He might say something along the lines that the supercomputer in true reality, running the simulation that we're experiencing, might involve a data structure which encodes all the contents in a block universe. And therefore, for any two different slices of the simulation of the universe, the fundamental information lies in the relations between the entries of the data structure. Space, in this way, is then a secondary emergent feature that is a byproduct of the underlying real data of the universe. Nevertheless, Newton would become the market maker in physics, so to speak, and by imposing absolute space and time, he would thereby have an adequate foundation for the mechanics of macroscopic bodies. Interestingly enough, Immanuel Kant, the philosopher, would take interest in the nature of space-time aspect of the subsequent calculus debate between Newton and Leibniz. So here's something that might not seem at first blush to be directly connected to the conception of space and time enabling Newtonian mechanics, but I promise it'll come around in a moment, so bear with me here. So in ethics, Kant is known for the so-called categorical imperative, which is definitely a mouthful, but it roughly means the culmination of a system of morality that aims to be constructed through reason upon a secular foundation. And so for Kant, the first part of determining such a system of morality is framing the categorical imperative. So another way of stating what the end goal of the categorical imperative that Kant is looking for is he's looking for an unambiguously explicit and direct definition of morality. The first rational step Kant took was to frame what he was looking for as an unconditional moral obligation which is binding in all circumstances and is not dependent on a person's inclination or purpose. The next part of determining this system of morality, if you will, is to come up with a unique formulation that satisfies this framing. Because it's not good enough if we can have multiple formulations. We're not going to be slipping down the slippery slope of, subjective morality where, we're getting into Nietzsche and nihilism and all that quite just yet. This is not quite there yet, okay? So we're looking for a unique formulation that satisfies the framing for the categorical imperative. And this is Kant's categorical imperative, namely, act only on that maxim through which you can at the same time will that it should become a universal law. In other words, this is just the golden rule from kindergarten. Do unto others as you would prefer to be treated. This is Kant's categorical imperative, which he intended as a secular foundation for morality. However, and this is the connection to the theater of God of Newton, Kant's ethical framework implicitly presupposes an abstract, omnipresent moral arbiter that underpins the notion of universality and duty. Thus, the authoritative Christian God is transposed and embedded impersonally into the rationalized structure of the categorical imperative. Now, as I discussed in previous episodes, Immanuel Kant, staunch advocate of reason and rationality, of course, as we know him to be, Kant demonstrated the boundaries of using pure reason to grasp the nature of transcendental reality through his antinomy of space and time. Now, as a reminder, Kant had a total of 4 antinomies, which antinomies are just these kinds of paradoxical statements of a certain kind of logical structure that consist of a pairing of a thesis and an antithesis. So an example of an antinomy might be, and this is one I keep bringing up, If there's a barber who shaves everyone and everyone only who doesn't shave themselves, then does the barber shave himself? Now that's just an antinomy. It's not one of Kant's four antinomies of pure reason, obviously, but specifically Kant's space-time antinomy shows that one can validly reason that the world has a beginning in time and is spatially finite, while equally valid reasoning can conclude that the world is infinite in both time and space. Since these notions obviously contradict each other, Kant suggests that this demonstrates a limit or irrelevance of critical reason in providing insight into the transcendental ideal nature of reality. The contrast of Kant's staunch rationalism is, of course, empiricism, the notion that truth originates from sense experience. So here's a story for you. A man goes to the supermarket once a week and buys a raw chicken. Before cooking the chicken, he has sexual intercourse with it. Then he cooks the chicken and then he eats it. No harm, nobody else knows. Is what the man did wrong? And so if you're new here, I promise that my videos are about math, so here's a palate cleanser. Here in differential geometry, gang, we all know that rational numbers are the set of all numbers that can be expressed as the ratio of one integer to another integer, a rational fraction, if you will. Now prove that there is no smallest rational number, or in other words, prove that rational numbers can be arbitrarily small. Now, reflect on the difference in your thought process when I asked whether the chicken man's actions were wrong compared to when I just challenged you to prove that there is no smallest rational number. Now, I can't read your mind, and I assume that no one is undergoing a brain scan while watching this, and even if you were, I don't think any relevant data will be available for the purposes here. But nevertheless, I suspect that when you heard the story about the man and the chicken, you immediately felt a mixture with what perhaps you'd call revulsion or disgust. And the point is it's that feeling that tells you that what he did was wrong to you. Any verbal reasoning about your moral stance that may follow probably only serves to justify that initial gut reaction. In contrast, when you consider proving the arbitrary smallness of rational numbers, you likely shifted to a different, more analytical and logical thinking modality, distinct from the more intuitive judgment guided based approach used for the question about the man and the chickens. When justifying your view on the man's actions, you might even go so far as to cite an a priori moral authority, like a quote from a religious text, say, that condemns the act. But you likely wouldn't need to methodically consult such a text in order to resolve any uncertainty you had, being unable to decide on whether you think what the man does with those chickens is wrong or not. Rather, your response was instinctive, it was fairly immediate, and it wasn't a product of detached skepticism. I also doubt whether Kant's golden rule, or the technical, precise, rational formulation of the categorical imperative, would be most people's go-to when explaining their opinion of the man and those chickens. So, with this in mind, remember that the broader impact of the result of the Michelson-Morley experiment can be interpreted as empirically undermining the notion of absolute space as endorsed by Newton and Kant. Saying that the luminiferous ether does not exist is tantamount to rejecting absolute space, as no other phenomenological basis for defining an absolute reference frame had been proposed at the time of the Michelson-Morley experiment. Using the advances in math available at the time, namely the advances of Riemann, the advances of Ricci and Levi-Civita, Einstein was able to use these advances to determine the metric of the space-time continuum in such a way that the inertial forces on matter in motion result automatically. This non-Euclidean metric also holds for motion in accelerating reference frames, which give rise to the fictitious centrifugal and Coriolis forces that were a sticking point for Newtonian gravitation. For Einstein's general relativity, there are locally inertial reference frames only. So, of course, there are no globally inertial reference frames due to the curvature of space-time. And by the same token, this also means that gravity is inherently the result of the curvature of space-time. And in this way, gravity itself is also such a fictitious force as the centrifugal force and the Coriolis force. The same forces arise in general relativity whether the Earth is turning on its axis within the rest of the universe, or instead if the rest of the universe were rotating around the axis of the Earth. Thus, the revolutionary understanding of space-time of Einstein's general relativity transcends the original conflict of Ptolemy's and Copernicus's views. Various ideas about the geometry of space-time are canceled and refined, while other ideas, such as what happens when you drop a pound of feathers versus a pound of nails from the top of the Leaning Tower of Pisa, or the legitimacy of centuries of observed data about the orbit of Mercury. These ideas are preserved along the way to a more developed understanding. The understanding of gravity is not a lump sum accumulation of conceptual advances. General relativity is not widely regarded as a massive footnote to Ptolemy's geocentric model of the solar system. This ideological synthesis in general relativity embodies the dialectic of progress. So I've tried just now to illustrate this within physics with general relativity, but I've also already alluded to examples of the dialectical nature of progress more exclusively within either math or philosophy as well, respectively. Obviously, for instance, the term non-Euclidean embodies the outcome of rejecting Euclid's fifth postulate while retaining and advancing fundamental geometrical concepts of length, angles, and area. Hopefully, you can appreciate at this point the versatility of the philosophical notion of dialectic. I've brought up how a dialectical process of progress unfolds in the distinct disciplines of math, philosophy, and physics, but by these fields' very nature, progress or lack thereof in one area interacts with progress in the other areas. I've also touched on ideas from various other branches of philosophy. Now, at this point, I anticipate getting criticized as a crackpot. Everything I've just said merely shows that I'm clever enough to create a surprisingly internally consistent system, but I'm not clever enough to notice the pervasive circular reasoning that holds no ground for anyone but me.
It's totally made up.
People only watch my videos to see how deep the rabbit hole goes with me.
It's a made-up tale.
The only reason why I'm even bringing this up at all is because I must be secretly upset that people don't believe in what I'm saying or that I don't get enough attention on my videos.
It's fiction.
I'm a fraud who is intentionally deceiving people.
We made this one up. We got you.
Or maybe even if some people think that I can be decently smart at times, I'm funneling my energy in all the wrong places.
We made it up.
At best, I might be better suited for world building and fantasy writing.
This one was invented by a writer. It's fiction.
In fact, look out for a young adult YA novel.
Pure fiction.
No, I'm just kidding. I may be creative with words, but the words do little to mask shallow thoughts with little originality and no insight.
Not a chance.
I leave it up to the other members of the audience if they really think I'm a crackpot. But I think especially in physics, the conceptual advances and the experimental advances, particularly those related to measurement precision, are very related to each other. Indeed, the ability to understand and properly use measuring instruments, the ability to show orderly development from original concept, Keeping proper lab notes and being able to communicate these ideas to others is critical. However, even with a greater degree of education or access to resources, it is often the case that mistakes in measurements or interpretations of data leads to the demise of the endeavor. And my own measurement and lab skills can certainly be improved, as I have no publication record directly related to any of these concepts. I have no first author papers. I don't have a magic box with something incredible inside that can be leveraged into a business. And I am arguably doing nothing more here than posting weird science videos on YouTube. Diligent measurement skills are particularly important in view of the requirements of new areas along the lines of energy and propulsion. If I'm some uneducated crackpot, then you can probably find a real physicist doing hardcore math and so on and so forth who already made a YouTube video talking about all of these things and done a way better job than me. A person who meets the prerequisites to do this is still probably less inclined at the end of the day to pursue scientific advancement in an area that implies, say, a proof of concept for new technology in areas along the lines of advanced energy and propulsion. They still tackle difficult technical challenges, but not generally fundamental issues like gravity and primary energy. The likelihood of such a person being interested in topics like energy and gravity is thus greatly diminished. It's possible that by avoiding these supremely difficult areas, that these sorts of smart and capable people have been able to innovate in other areas, are thus already better funded, and the areas of advanced energy and propulsion get ignored. Additionally, a technological breakthrough in these areas could immediately lead to the imminent nuclear destruction of human civilization as we know it. This would obviously be a national security concern. The issue is not paranoia that the aerospace and fossil fuel industries would be disrupted by revolutionary breakthroughs in active gravity manipulation or energy. The potential disruptive effect of a revolutionary energy breakthrough to the current fossil fuel industry is obvious. On the other hand, gravity is the bane of all aerospace endeavors since it pulls all objects down towards the Earth's surface. Similarly, in deep space, there is no ambient medium to push against in a deep space vacuum, so jet propulsion requires a craft to carry propellant to eject in order to provide momentum. This becomes a vicious cycle as more propellant is needed to be able to carry more propellant and allow the craft to travel possibly even further. If a breakthrough mechanism could enable new technology, it seems to be in the aerospace industry, for example's interests, to pursue such a mechanism and building the subsequent technology. The problem here might be that precisely how scientific knowledge of any kind interacts with technical processes and institutional structures remains an open question. However often technologies appear to cause changes, technical change itself is frequently not the cause, but rather the result of underlying changes in the availability of raw materials, in the structure of firms, and in social norms and economic conditions. Consider the material of steel, for example. Steel skyscrapers abruptly emerged circa 1890 in one country only. In other words, the emergence of steel skyscrapers is not just about a greater understanding of steel as a material and being able to metallurgically manipulate steel into usable forms. The emergence of steel skyscrapers is also about the economic conditions that incentivized workers to build the skyscrapers and incentivized companies to be structured so that their offices can operate in the skyscrapers, and that social norms were such that people were willing to commute to work in a skyscraper as part of their daily lives. This did not take place worldwide at the time. To be somewhat more specific, consider, for example, materials that have a piezoelectric property. In particular types of solid materials, a mechanical stress being applied to the material results in an electric charge or measured voltage. The word piezoelectricity is in fact derived from ancient Greek piezo, meaning to squeeze or press, and electron, which is referring to amber. Thousands of years later, the Curie brothers, Jacques and Pierre, found that squeezing crystals, such as quartz, results in voltage proportional to the squeeze force strength. They did not, however, predict the converse effect, which is that applying an electric field to the piezoelectric material results in a mechanical stress within the solid, but this is indeed the case. As a matter of fact, modern piezoelectric transducers exploit this dual principle. A single piezoelectric element can be modeled as a transmitter where an alternating electric field is applied to generate a wave, and a receiver that collects waves reflected back from objects, and these reflected waves can be processed into an image, perhaps, depicting objects in the range of these emitted waves, or transmitted waves. The piezoelectric mechanism is thus electromagnetism influences matter, which influences space. Recall that general relativity shows that space and time are in a sense equivalent. So if there are known materials that have the property that electromagnetism influences matter and then influences space, then as perhaps suggested by the results of general relativity, what would it take for a material to have a property where electromagnetism influences matter, but then this influences time? Or why could it definitively not be the case that a material could have this property? For now, table other related questions and concede for the moment that one piece of the puzzle is to determine what a mystery material, let's say, with this capability of electromagnetism influencing matter, influencing time would be like. Another piece of the puzzle is powering the technology that involves this material. Presumably, this is going to be a source capable of high energy and or energy that is directed in a very specific, sophisticated way. One possible approach to coming up with a way to power technology involving this mystery material might be through quantum theory. Don't think, just calculate. Quantum theory predicts that the vacuum of space throughout the universe is filled with electromagnetic waves, random in phase and amplitude, propagating in all possible directions and with a cubic frequency distribution. This differs from the cosmic microwave background radiation and is referred to as the electromagnetic quantum vacuum. So somehow, if you could just take advantage of these random fluctuations of the electromagnetic quantum vacuum, then the taking advantage of we would refer to as cumulatively exploiting the 0-point field. And you're extracting energy from the taking advantage of these random fluctuations of the electromagnetic quantum vacuum. So, furthermore, even though this 0-point field or ZPF energy seems to be an inescapable consequence of quantum field theory, its energy density is so enormous that it is subtracted away from calculations by ad hoc approaches such as renormalization. This is in stark contrast to physically observable effects such as, for example, the Casimir effect, where an attractive force exists between two uncharged metallic plates held very close together in a vacuum. Therefore, exploring the possibility that ZPF energy is real lends itself to a physical interpretation that the ordinary world of matter and energy is like foam atop the quantum vacuum sea, as well as to the possibility that the ZPF can result in a novel power source or power a novel propulsion system. This is the notion of exchanging energy with the quantum vacuum. However, Einstein's most famous E equals mc squared, which is not general relativity, implies that, in principle, energy can manifest as mass. Therefore, a successful exploitation of exchanging energy with the quantum vacuum might also enable the extraction of mass from the quantum vacuum as well. This could perhaps then be the method of procuring the material needed in the other piece of the puzzle, whereby electromagnetism influences matter and that matter is capable of influencing time. This possibility is the crux of the national security risk due to the uncertainty in the outcome of purely scientific innovation. Currently, international stability is predicated in terms of pure physics upon a few things. First, the world is covered with nukes. Second, nukes can be launched from submarines. Third, let's say you ignore the submarines for now. If a nuke is launched at the United States, it's going to come from the direction of the North Pole. as a nuke flies, it has progressively less latitude to change direction to throw off anyone tracking the nuke from figuring out what its end target is. With this in consideration, once the nuke gets fired off its launch pad towards the United States, the president has 6 minutes to decide what to do. That incoming nuke could target any of the nukes that the United States has, so it's a use it or lose it policy. In other words, if the president decides in those 6 minutes to fire back, then all of the United States nukes will be fired. Once you add back in the second given, which is that nukes can be launched from submarines, the time until a nuke hits is now far less than 6 minutes, and the physical limiting factor of deterrence comes down to the fluid density of water. Basically, torpedoes can only move so fast underwater, and nuclear submarines are notoriously difficult to track. It has been said that it's easier to find a grapefruit floating in outer space than trying to find a nuclear submarine in the ocean. Therefore, within 6 minutes of a nuke being launched, enough other nukes would be launched to basically guarantee that human agriculture will not be feasible for at least the next 10 years afterward if there's anyone still left. In short, being able to extract the material by exchanging energy from the quantum vacuum to create a device that can effectively instantaneously travel anywhere on Earth and potentially unload an existing nuclear weapon payload is a big problem. However, events such as the 2017 Tic Tac footage are akin to a Sputnik moment, where scientific and technological breakthroughs will follow in light of the demonstration of proof of concept independent of the known origin or purpose, you could say, of the Tic Tac observable. For me, what this distills down to is that the theoretical physics of a proposed UFO or UAP mechanism implies an opportunity for metamaterials to be a possible solution for what the mystery material is like or could be. What I said previously about the piezoelectric effect alludes to how the problem of quantum gravity is perceived to be intrinsically intertwined with the unification of the fundamental forces. The gravity due to general relativity at a quantum relevant scale is negligible, but something akin to quantum gravity would be needed to affirm controlled emergent gravitic effects from physical phenomena at a quantum scale. This is obviously a huge, massively difficult open problem, and I am a nobody. This is my current wording of part of what makes quantum gravity tricky to describe mathematically. Consider a material of n layers which is irradiated so that the measured force of gravity on the material due to the Earth is counteracted. If you bound the section of material where the radiation is incident, the exotic emergent gravitic effect, let's say, due to the radiation, must exceed the entire sum of m of the body of the material for this to work, where m is the mass. You could perhaps say of the atomic structure, so you're summing over the individual atomic constituents of the material, let's say. However, under the conditions where this exotic emergent gravitic effect exceeds the force of gravity due to the curvature of the Earth, we cannot easily, immediately, mathematically distinguish from the case of what happens if, say, a single layer of the material was then removed. Why did you even need n layers to begin with? Or why are n-1 layers not sufficient to achieve the same effect? A correct framework could provide a mathematical insight into these sorts of questions, perhaps. This mathematical ambiguity could be made sense of physically if the masses of the atoms were widely separated from each other, relatively speaking, and subjected to comparable radiation conditions, and then for this to be compared with measured gravitational effect under actual conditions, or, in other words, an actual viable proof of concept. As far as I know, this also hasn't come to fruition experimentally in the open. Here's another thought experiment. Assume we want to examine an object located within a small box. To determine the object's size and location within the box with progressively greater precision, we commensurately reduce the size of the box. However, according to Heisenberg's uncertainty principle of quantum theory, then the particle's momentum is determined less and less precisely, naively implying that the particle is becoming even larger. Yet, As the momentum increases, so does the energy. And therefore, by the mass-energy equivalence of E equals mc squared, so does the object's mass. According to general relativity, high mass concentrations make it increasingly difficult for light to escape this mass, which ultimately leads to the formation of a black hole event horizon. The radius of this event horizon is proportional to the enclosed mass, and from whose interior no information can escape. Thus, to recap, as the box became smaller, the object became more localized, but the radius of the object's event horizon also became larger. Therefore, at some point, the object disappeared behind its own event horizon and became essentially unobservable. If there's an experiment resolving all of this, will somebody please tell Ed Witten? This is the same Ed Witten who was asked in 2014, in his opinion, what are the main challenges or problems in theoretical physics at the moment? And he answered, quote, "Personally, I would like to understand what string theory really is," end quote, Ed Witten. Nevertheless, math is already capable of making rigorous, well-founded statements about how quantum gravity may possibly be. Whether anyone is up to the task of doing the heavy lifting is another question. In the 1970s, Bryce DeWitt took the newly developed toolkit of quantum field theory and applied it to gravitational interactions. But it turned out that gravity without any other additional source of matter is perturbatively non-renormalizable. This implies that making further and further perturbative corrections to interaction processes of theoretical massless gravitons, this leads to an infinite number of counterterms, each with its own corresponding infinite number of free parameters, which need to be considered in order to obtain finite results. Meaningful predictions about gravity at increasingly high energies as such have not yet been achieved. So, to start getting into explaining what this slide on the screen is about, if I were to come up with a shopping list of what this exotic craft, this mystery material would accomplish, it would include the following. The material of the fuselage of the craft is a metamaterial, that is, the material is engineered to have properties not typically found in naturally occurring materials, such as manipulating time. The key property to engineer into the material is the ability to manipulate the local space-time metric near the material in a controlled way. There is a distinction between what I just described and what the phrase space-time metric engineering means. Space-time metric engineering might more properly refer to the creation of wormholes. For example, modifying the metric of space-time so that two classically very distant star systems are basically spatially linked, like us and Zeta Reticuli or the Pleiades or something like that, Alpha Centauri. The local space-time metric manipulation I'm describing would allow for a craft to have an internal compartment, let's say, with its own internal space-time metric, but that is coupled with the external fuselage. And so this is what I have in the top left of the slide here, and this is bringing back what's from the very, very beginning, like an hour ago of this video. This is not a technical double bubble. It's a bubble within a bubble because, as I had mentioned with the double bubble theorem and the whole, common circle and the angles matching at 120 degrees, that's not what this is. We have to get the terminology correct, that way people can understand us, right? Because of this setup, the fuselage can manipulate what I'm going to call for now the global space-time metric, so that an external observer sees a UFO basically shoot off like a bullet from a gun. And in this scenario, an external observer of this UFO could take a video recording, let's say, and then they could do a frame-by-frame analysis of the video footage afterwards, and they could empirically measure in this way the apparent acceleration of the UFO they saw, and thereby determine that the classical force that an occupant of that UFO or UAP would be subject to is presumed to be experiencing would blow them to smithereens. This classical force would be something maybe on the scale of something upwards of hundreds to thousands of Gs, which is obviously beyond what humans can tolerate. The metamaterial engineering of the internal compartment allows for an occupant to be following possibly a rest-like or a free-fall-like space-time metric, and that compartment is coupled within the outer fuselage, and then the outer fuselage is basically falling away from wherever it was and falling towards wherever, whenever it's going. So by falling, I of course am alluding to meaning not just in space, but in space-time. Now, take for example a Leibnizian view of matter, so that we can therefore in this view take the constituent components of the material of the craft to be like Knex pieces. A Hoberman sphere is an expanding sphere comprised basically of scissor joints, and this Hoberman sphere can be made from Knex. Geometrically, the angle subtended by a scissor joint is constant regardless of the angle between the two halves of the scissor joint. So opening and closing the expanding and contracting Hoberman sphere is tantamount to freely tuning the angle between the halves of the various scissor joints in the Hoberman sphere to go between the set of angles corresponding to the open configuration and the set of angles corresponding to the closed configuration. So the engineering of this mystery material to attain a passive, locally perturbed space-time metric within a fuselage that can be actively driven to then effectively travel to other regions of space-time might amount to an analogous tuning process. This would explain how entering a UFO or UAP that looks, say, from the outside like the size of a four-door sedan, a car, how that once you get inside, it could be made to feel like entering a small apartment or a small home, or it could even feel like being pulled into a manhole at the center of the 50-yard line in a football stadium, where the force lines of gravity are anti-parallel or upside down relative to how they are where you were when you enter. So as far as the mechanism of the actively driven travel to other regions of space-time goes, I mentioned before in another episode the possibility of relativistic rotational frame dragging, which is also known as the lens steering effect. The craft that would be using this for its mechanism implies that the craft, of course, operates analogously to a submarine, displacing space-time around itself to travel to different regions of space-time. And this is a good time to point out that the natural lens steering precession of the planetary mass of Mercury is very, very small. A common theme in this UFO UAP craft exploration is that cosmological scale energy and gravitic effects are playing out basically on a gas-powered scooter scale. The hope of this actually working might be that the metamaterial resonates in a way that the coupling between electromagnetism and the gravitational field is stronger, so that an EM input can possibly manipulate gravity and or space-time. The key is the metamaterial resonance. However, this may involve actively controlled, highly sophisticatedly patterned light dispersion within the structure of the metamaterial. This is a challenge because general relativity seems most commonly derived for test particles in vacuum-free space rather than in continuous matter. When general relativity is worked out in continuous matter, the easily available low-hanging fruit solutions commonly sought are often only relevant in cosmology, not solid-state room temperature metamaterials. During operation, the metamaterial might be pumped with energy the same way that laser beams with particular characteristics are produced based upon qualities of the optical resonator of the laser device, whereby only light with a certain energy and wavelength can escape the optical cavity and get focused by an external lens into the desired laser beam. If a civilization from another star system created any such a craft, they would still be using basically the same elements available from the periodic table present in the universe for building blocks. Naturally occurring sources of elements will vary somewhat by particular isotope abundances, depending on what star they were made in. The elements we know, such as silver, magnesium, zinc, bismuth, gold, etc., would still be what they are to us even if from another civilization's UAP material. This depends, of course, on the holographic or interdimensional extent and nature of reality. The origin civilization of a UAP phenomenon could be non-planetary in the aspect of their domain of existence, that they interface, interact, share, or commune with us in our universe. For philosophical simplicity's sake, for now, assume that they're from a distant constellation not unlike ours, but that perhaps they reached our level of progression thousands or millions of years ago. A different time machine building, space traveling civilization in the universe might differ in the natural availability of certain elements, isotopes, and materials on their planet of origin. For instance, a relatively disadvantaged planet might not have any naturally occurring magnetic materials. Not having magnets available could obviously impede the pace of developing an understanding of electromagnetism. Conversely, a well-endowed planet might have naturally occurring heavy element isotopes within the theoretical island of stability that only single-digit numbers of atoms have been synthesized in massive particle accelerators on Earth so far. Maybe these elements aren't involved in the fuselage of the craft, but are critical for a radiation source which pumps energy into the metamaterial fuselage or otherwise. If a civilization were part of a star system and on a planet with a natural abundance of these heavy metals or materials involving them, it would be the opposite situation from us to a planet without natural magnets. Instead, it is we who are ignorant of what might seem like obvious features of nature to a civilization that developed with a different material endowment. More of what can perhaps arise that's beyond us from a metamaterial situation is analogous to the shiny metallic appearance of a Chrysina limbata scarab beetle. The Chrysina limbata scarab beetle has a distinct reflective silver metallic appearance, but this beetle doesn't grow a molten metal coating. Rather, the appearance is the result of the thin film interference within the layers of chitin of the shell of the beetle. Pure chitin, of course, is not a metal, but is a nitrogen-modified polysaccharide resembling glucose that is ubiquitous in arthropod exoskeletons. Different insects' genetic programs modify the components of the chitin to make composite materials specific to the needs of their evolutionary niche. Specifically, the genetic expression of chitinous tissue on Chrysina limbata forms what is called a chirped surface. This is a kind of complex multilayer such that each progressive layer decreases in depth, and as the thickness of the chirped spaces varies, different wavelengths of light are reflected between the stack of layers. As a result, around 97% of the visible light spectrum is reflected by the Chrysina limbata coating, giving it its metallic appearance. The bottom line is that just because it appears metallic doesn't mean it necessarily has to be made of elemental metals, metalloids, and so forth. As far as things go for actual UAP, of course, I don't know for sure, but I put this light bulb here as a concept holder. Light bulbs have a filament inside a space confined by optically clear glass that's commonly filled with gas. When a particular sort of filament is electrically stimulated, a light is emitted. And by surrounding this fundamental phenomenon in a chamber of a particular sort of gas, the initial emission phenomenon is amplified through scattering so that one has engineered a diffuse source of light that's practically useful at a human size scale or form factor. There could be a reactor or warp drive source instead of a filament element that excites an inner space and irradiates the fuselage material layers so that effectively only gravitons with particular characteristics, say, can transmit outside the fuselage, akin to a cavity-stabilized laser. Alternatively, this could take place using spooky telekinetic action at a distance quantum effects, like the Aronov-Bohm effect, or some clever way of setting up the constructive and destructive interference of the source energy so that it focuses exclusively directly in the metamaterial, etc. So that's what the picture of the longitudinal and transverse waves down in the bottom right are. Ultimately, the metamaterial will support a response tailored for given incident electromagnetic wavelength and angle conditions. By the material's fabrication, a variable form factor perhaps includes the local dielectric constant of the surface of the material. Dielectric, of course, means the ability of a material to store electric energy in an electrical field. Elemental bismuth is an example which was on the previous slide. These are some crowded slides. I do apologize about that, I get it. Elemental bismuth is an example of a material with a property analogous to being dielectric. This analogous property is called diamagnetism, where applying a magnetic force to the material, in this case bismuth, results in an induced magnetic field in the opposite direction, leading to a repulsive force from the external magnetic source. With a suitable configuration, levitating bismuth sculptures can be made where the weight of a piece of bismuth is balanced between a magnet above and below the bismuth. That's what I have pictured here. Similarly, an analogous emergent property in materials could involve the ability of a material to warp the curvature of spacetime. With a general enough material, like how many types of computer chips are all fundamentally made from silicon, different functions of frequency, polarization, or wavefront shape of incident radiation on the right material could accomplish exotic multi-objective design requirements with a highly robust topological structure. At present, it seems possible or plausible that these very well could be plasma metamaterials. Plasma, of course, occurs when enough energy is injected into a material to break up its atomic structure. In the bottom left here, we have a plot of the density of electrons in the plasma versus the electron temperature, with various examples at the location representative of their density and temperature. In this depiction, everything from lightning, metal, since electrons are delocalized in metals, aurora borealis, and the Sandia Z machine are all shown here as examples involving plasma with different densities and temperatures. Someday, something we would at present refer to as a UAP, but built on Earth at some time in the future, might be definitively placed somewhere on this graph. Furthermore, particles in high energy states may be associated with spinning or vibrating very rapidly. Some surfaces, when rotated about an axis, result in surfaces defined by the space confining where the original volume can occupy, in contrast to the shape confined by the resting surface. Coordinating this within a highly energized material could lead to even further emergent functionality in the context of extremely complex electromagnetic dispersion and dissipation. And then this is now where I'm going to talk about what's like the bottom center, bottom right, and then the right middle of the slide here. This is about moire materials, so layers of graphene, carbon, hexagonal lattices. So, like I just said, if you start off with bilayered graphene, where each layer is a honeycomb lattice of carbon atoms, and a twist is applied to one of the sublattices so that a pattern of what emerges appears like light and dark spots. This is a particular kind of material where you can tune and get some maybe cool emergent properties. So when you twist one of the layers like this, the emergent lattice is called the moire superlattice, because it's a lattice that comes from the other lattices, right? The light spots are parts where the layers are directly on top of each other, and in the bottom right, that's the AA case. So for example, it's at the center of wherever your twist is when you're trying to make your moire superlattice. And then conversely, you have these dark spots, which are where the carbon in one layer is at the center of a hexagon ring of carbon in the other layer. And that's pretty much what's shown in case AB in the bottom right there. Now, when you twist at the so-called magic angle, then properties emerge related to the tunneling amplitude of an electron in the graphene lattice. Now, Perhaps an analogous layer twisting is involved in the operation of one of these hypothetical craft to accomplish any one of the exotic functions I've already mentioned. And a lot of this implies that with current industrial techniques, getting anywhere remotely close to fabricating prototypes and iterating on design after design with improvements would not only require vast input resources destined to be the material of the craft, but also water, energy, and human capital. And it would possibly involve advanced lithography methods and much, much more. But the image I can't shake from my mind is akin to what it looks like pulling a bismuth crystal from a molten crucible as the bismuth rapidly cools and hardens, combined with a kind of stenciled hoop ring with a handle like this kind of soap bubble wand, and this gray humanoid looking being waving this soap bubble wand in the air so that a metalloid appearing UFO UAP materializes like a soap bubble from the hoop. And thus, the craft is fabricated without it ever touching the ground once. And the whole time that this happens, it's like Kids by MGMT is telepathically playing in your head. Anywho, humans throughout time have been fascinated by the phenomena in the nature that surrounds them. Physics and math together make the tools to begin to outline an approach to start understanding these phenomena and ultimately build technology involving them. These insights and new technologies often aren't developed solely by the results of math that can be done by hand using pencil and paper with what can be remembered by the mind of a sole individual. Take predicting the weather, for instance. A sizable Doppler radar is constantly powered on collecting data, or else you're losing a lot of money. We rely heavily on computers to handle this high throughput stream of information. At some point, someone likely sat down and synthesized knowledge about atmospheric chemistry, models of wind flow, etc., in terms of physics equations, and produced a computer program that numerically processes data comparable to real-time Doppler radar data. And this initial program might have taken, say, a week to process weather data for a square mile location that spans 24 hours of data collection. After that, people gradually expanded on that work so that eventually it takes less time to process what data is being represented, a larger area can be accounted for, the algorithm is adapted to a scaled platform with more compute power, real-time performance is engineered, and frameworks are put in place so that people can see colorized images of the live Doppler radar images through an app on their phone that obviously isn't locally processing the local Doppler radar data. Along the lines of what I stated earlier towards the beginning, math is sterile without an application in science or engineering. Computer pipelines are also very important for realizing the hard gains afforded by theoretical results. I bring up the weather example to illustrate this point. In some domains, such as geology or civil engineering, you can have robustly detailed models of something like the vibration of the earth. When you model a well, you're digging, let's say, to make maybe a risk assessment or something, but a lot of the fancy math will end up not making a difference, and something like only a few linear terms are needed in order to make an actionable business decision. Putting this broad generalization about engineering math aside, differential equations are ubiquitous in scientific applications informed by physics. And this often involves a wave equation or something similar to a wave equation. After you come up with a map of the territory of your problem in terms of partial or ordinary differential equations by themselves or perhaps in a system, and you have a plan that you're fairly confident you won't drive off of a numerical cliff speeding at 120 miles per hour, then the next step is to actually sit down to implement your solution as an algorithm in code that you can run on a computer or computers that exist somewhere. Premature optimization is, of course, the root of all evil, and the majority of people are not proficient at writing enterprise quality code day in, day out when their focus is the science or the end goal of the technology they want built. Things like ill-posed inputs to functions, infinite loops, and memory management appropriate for the intentions of the user invariably need to be handled to enable iterative progress developing tools in a given niche application or subject area. As such, the state-of-the-art group theoretic solid-state physics algorithms are implemented in something like Mathematica. Any software engineer or computer scientist could easily understand that Mathematica is a far cry from a tailored, polished, high-performance implementation in a language like C++ that can maximally leverage hardware like GPUs. Preliminary results will inevitably come from established libraries in Mathematica and using systems like GAP, where GAP stands for groups, algorithms, and programming. It's like last time I used it was like it's like the terminal interface, but it's got like, group theoretic commands baked into it. But riding a tricycle in a sandbox is different from setting a land speed record on a motorcycle or biking across America. At some point, a preliminary result that is either only in 2D or has a coarse resolution in space or in time or both, and the desire will be to generalize to 3D, make the grid resolution finer, etc. And this will grind things like Mathematica and MATLAB to a halt, basically. To go back to the weather analogy, do you really think that the Doppler radar processing has real-time MATLAB running under the hood in every major metropolitan area's weather station? No, I don't think so. To me, this is the incentive to take highly mathematical algorithms and numerical frameworks from a rudimentary proof of concept in Mathematica or MATLAB and adapt them to something like C++, where the gains in performance make previously out-of-reach analysis feasible. So maybe what it takes is merging computational group theory and computational partial differential equations to simulate radiating different crystal material structures and assessing whether novel physical results arise. Macroscopic electrodynamics in media would presumably be governed by a tensorial formulation of Maxwell's equations in terms of partial differential equations in, say, a flat spacetime geometry. In these sorts of solid-state atomic structure type problems, dissipative and dispersive characteristics are essential, and these are handled by complex valued tensors. Suppose we transpose the formulation of partial differential equations I just sketched into a different PDE with a curved space-time metric. This could be done maybe using a version of the Laplace-Beltrami operator, which I read about from the Kreisig book just a few episodes ago. This involves introducing a metric that in effect subsumes what is mathematically accounted for by these other electrodynamic metrics in terms of tensors for effects such as permittivity and permeability. Not only is formulating this new metric from complex valued dissipation and dispersion not obvious, but the physical interpretation of this new complex valued metric still needs to be provided as well. If you got a hold of that and incorporated the group theory details in an elaborate computational framework, maybe you could verify what material composition would be sufficient to result in exotic novel propulsion or energy technologies by demonstrating quantitatively the emergence of a physical result, perhaps related to electromagnetic resonance, involving high spin or high vibration electrons delocalized in the crystal lattice of this mystery material. If you did this, then you'd be a step closer and you could start to think about how to meaningfully synthesize and fabricate this mystery material. So, all right, now let's get into the reading.